four important statements we started with. Actually, the lesson is electrostatics, children. But before we actually go into that lesson, we have to understand the meaning of fields and forces. In that connection, I made four statements. Electric fields are produced by both stationary and moving charges. Electric fields apply force on both moving and stationary charges, whereas magnetic fields are produced only by moving charges, and they in turn exert force on moving charges only. But all these statements are true when you are watching from the ground frame. Let us not get into the tangle of changing the reference frame for now, because that will trouble us for the beginning. So anytime when I said stationary charges are forming electric field, what I mean to say is I am standing in the laboratory and I'm at rest there, and then I'm watching some charges being formed on a metal object, and around that my understanding is that there is some invisible thing called field, and this field will apply force if I bring one more charge into that. That one more charge we bring and test the presence of field is called test charge, and the one which is causing this field around itself is called source charge. And the whole of electrostatics or electricity and magnetism is about fields and forces, children. Now I'll continue with the examples which we started yesterday. Now I want you to answer the questions as usual. There are two, I'll just use a different color. There are two current carrying wires, children. Now, like yesterday we talked, please mute your audio. Sushma Vaddepalli, mute your audio. Right. Look, this requires a lot of discipline, children. Right. Now look at this. You are standing here in the lab and you're saying that there are two current carrying wires. So as usual, tell me, what are the fields and forces?
So there's magnetic field on around both the wires.
Yeah, correct.
And
tell me, Emma, come on.
And there's magnetic field, magnetic force exerted in both the wires.
On each of it. That's correct. What Ramya says is 100% right. So what was your idea, Manasa, when telling this?
So wire exerts magnetic fields. I mean,
no, in wires actually there are
moving electrons.
There are moving charges.
Moving charges.
Moving electrons, Amma, basically. Huh?
Yes.
So around that moving electron, there will be magnetic field.
Yes.
And this wire has no electric field, Ramya. What was the reason I told you?
So because the net charge is zero.
Very good. Nice. And how about others? Somebody entered now with some kind of a code. I want your names, children. I'm telling you, this class can be made more interactive than in a regular class, believe me. And you sit at your place and I'm sitting at my place. Huh? In the middle, you can have tea if you want without getting distracted. So in a cool kind of an atmosphere, you can actually learn subject in a big way. So for that, you need to talk to me. But for that, you need to identify yourself first. You cannot enter with codes. Do you follow? Name your Zoom ID with your own name. Okay? All right. Now tell me. Ramya was telling it properly. So you should write this one. What is the answer you write for this? Please keep writing along with me. Around each wire, do you have some notebooks with you? Preferably that long notebooks, long white pages notebooks. Generally, I prefer this classmate or some good notebook, premium notebook you need to have. And remember, this book which you write after my lesson will be your reference book for your engineering also. So that much importance is there for the class notes. For you to feel confident, but not to boast about myself, I'll tell you one thing. What is not there in the notes is not going to be there anywhere. So that much comprehensive nature of the notes and the subject will be there with you, believe me. All right. People are still coming. Children, you have to be on time. So around each wire, there is magnetic field. Each wire experiences magnetic force. Experiences magnetic force. Yes, Pawan, where are you from? Yesterday you were there? I don't know. What's your name? Your full name? Pawan. Which college are you from? All right. Now, another. This is fifth one or fourth one. Yesterday we did 4, I believe. This is fifth one. Yes, Rishita, tell me what do you want?
Sir, will the wires attract or repel each other?
Here, if the currents are in the same direction, they attract. If the currents are in opposite direction, they repel them. We did not show that forces at. We'll come back to that anyway in future. They attract.
Okay, sir.
Okay, right. And then another example I'll give you. Say, for example, we have a horseshoe magnet. Mute your audio. Some voice is coming from Vijay. Vijay, mute your audio. Right. This is North Pole, this is South Pole, for example. Here, I place one electron at rest. Now, Sihit, tell me what's going to happen. The horseshoe magnet forms.
Sir, nothing will happen to the electron.
Yeah, nothing will happen to the electron, but we'll say like this. Magnet forms what? Magnetic field. Electron has electric field around it and no interaction, right? And our first statement was this: magnetic fields cannot apply force on stationary charges. Now you can have a little reasoning also. The magnetic field doesn't apply force on the electron because electron has no magnetic field around it. Our modeling is this: magnetic field interact, electric field interact, right? So since this electron has no magnetic field around it, it doesn't experience a force because it doesn't experience force because of the magnetic field formed by the horseshoe magnet. All right. Seventh one. Look at this. The same horseshoe magnet again. Vijay, some voice sound is coming from your room. Vijay, is somebody else attending another class there? Your sister or somebody?
No, sir.
Well, mute the mics. When you're talking to me, open it. Otherwise, that will disturb the class and my concentration as well. Now, electron is moving like this, for example, children. What's going to happen?
Says there will be interaction between the horseshoe magnet and an electron.
What kind of interaction that is?
Magnetic
Magnetic force.
Magnetic interaction. Good. Now you started using the right words, children. There is magnetic interaction. But around the electron, there is both electric and magnetic field. Around the electron, there is electric field and as well magnetic field. And the horseshoe magnet forms only
magnetic.
Yes. That's what you should write.
Sir, do they attract?
Which one?
Horseshoe magnet and electron.
Here, of course, North Pole, I'll tell you, there's a rule for it. This is the direction of B. Actually, it bends which way I can tell you, attraction or whatever you can decide, that's not a big deal. And this is the velocity of the electron. V cross B will be like this. This is electron. So V cross B is into the plane. And on the electron, that force is outward. So it is neither attracted nor repelled. It is going like this. Okay?
Sir, sir,
Yes, Anshuman.
sir, around electron there will be no interaction, no, sir. Then you told it there will be both electric and magnetic force.
Electric and magnetic force, did I say, child? Around the electron, there is electric field and magnetic field, I told. Around means field will be there. Around the electron, there is electric field and magnetic field. But the interaction is only magnetic interaction. That means the electron will experience a magnetic force. And bar magnet also experiences, sorry, this horseshoe magnet also experiences, but that doesn't move because of heavy one. So electron will deflect here actually. Electron is neither going towards us nor going towards north. It is coming back, coming perpendicular to the plane. That comes with more mathematical explanation. V cross B, if you know, if somebody has done already, Q V cross B will tell you the direction of force, children. Like even in the cross product, you could have done in first year itself. I teach those things even in first year. But here it's not attraction. Whoever was asking, who was that asking that? Who was asking that question, child? Tell me.
Sir, Srihit, sir.
Yeah, Srihit. There's no attraction business here. There's a deflection. Okay.
Okay, sir.
Right. Now, can I change the screen, children?
Okay, sir.
Yeah. Now, there are two magnets, for example. North-south, some south-north. So around each magnet there is magnetic field. Around each magnet there is magnetic field and there's a magnetic force between them. This is what's happening here. All right. And somebody else was asking a question some time ago. What's the number I should give for this in the terms of the examples? 7, I think I've given here. Now 8. I'll put a 9th one here. This 9th one is yesterday Ramya or Rebecca, somebody was asking, look at this. I have a bar magnet and some iron piece is brought near it. Remember it. Remember here, around the iron piece, there's no field in the beginning. What do you mean by in the beginning, children? Srihit, can you tell me? When this magnet was not brought near it, iron piece has no magnetic field around it, no electric field around it.
Yes, sir.
Electrically neutral this is. That means no excess charge here. Electrically neutral. And even magnetically also neutral. In iron, there are tiny magnets, children. But they're all arranged in a very random way. So there's no net magnetic property with the iron piece. This we'll discuss in more details in what we call the magnetic properties of materials. And some of you must have heard of ferromagnetism, ferrimagnetism, diamagnetism, paramagnetism in chemistry. This iron is a ferromagnetic material. In this, there are regions of magnetic fields, which are called domains. In one domain, tiny magnets will be arranged like this, but they're all arranged in a very random manner. So there will be no net magnetic property around the iron, but there is magnetic field around it. And I want you to remember that even the bar magnet's magnetism is because of the moving charges inside it. That idea first you like, more details will keep coming. What is that idea? Don't ever think that the magnetism of bar magnets is different from the electromagnetism we talk. It was some habit like that for people previously. Permanent magnets like iron and nickel, whatever, and electromagnets are separate. People were thinking, but remember, Maxwell. We owe to Maxwell, Ampere, and one or two other scientists who actually helped us understanding that the magnetic field and electric field are similar. Our charges only produce electric and magnetic fields, they told us. So when you look at a bar magnet, never think that it is something different from the magnetic field formed by moving charges. Even inside a bar magnet, there will be circulating electrons which are unpaired or partial d orbitals, partially filled d orbitals in a ferromagnetic material like iron, which actually contribute to that current, net current, and net magnetic property for the material. So here, no magnetic field around the magnet, magnetic field around the magnet, and no field here. But the moment you brought, the field will be created here. Field will be induced, let me say. Net field will be induced.
The magnetic field around any magnet is due to the moving charges in the magnet.
Circulating charges, nothing else. So there is only one idea now. What is that one idea? When you have a magnetic field formed, that is because of moving charges. Ramya?
Yes.
Anytime, just take it for granted now.
Yes.
First get into the mood for it. Probably I'll talk even more about these things as we keep moving in the lessons. So if there's a bar magnet or Harshaw magnet or some round magnet, some spherical magnet or some electromagnet, the microscopic reason is only the moving charges and nothing else. But why some materials are non-magnetic, why some materials are ferromagnetic, all that will come little slowly. But remember, in a ferromagnetic material, these things will be there. There will be regions of iron material where small magnets are arranged in a particular way, which is called a domain. And many domains like this will be there. They're all randomly oriented. So no net magnetic property for the iron piece. But the moment you bring a bar magnet, that will create net field inside, and these fields interact, and that's why there is an attraction here. So these are the 9 examples which are very, very important for us. 9 or 10, I don't remember exactly.
Yesterday when we were talking about the comb and the paper, so is the paper considered as a particle or an entire a neutral object?
For what reason I should consider it as a particle? Tell me, Ramya.
Is it a moving charge or station?
No, I'll tell you. Since she is asking, I'll tell you in a proper way. Just listen to me. Did you do anything called dipole, electric dipole, Ramya, in the classes? Do you remember anything?
No, sir.
Not necessarily. Okay, don't worry. In a uniform electric field, whatever it is, you suspend a dipole, it will only turn. It experiences a torque. But in a non-uniform electric field, a dipole is what, Ramya? H2O is a dipole, believe me. When I have a glass of water, when I drink a glass of water, as a physics person, I think that I'm drinking many arrows like this. Each arrow represents one water molecule, which is an electric dipole.
Yes. Yes, sir.
H2O chemistry, you don't know H2O structure? HOO, some bond angle of 104 degrees, I don't remember exactly. huh? Due to the difference in the electronegativity values, partial plus delta, minus delta charges are formed. All that, don't you know?
Yes, sir.
So that H2 is a dipole, electric dipole. It's like a plus Q minus Q together. In a paper, in water, of course, there are dipoles already formed, but in a paper, this is an insulator. You cannot take out electrons from it. But once you rub this comb with your dry hair, electric field is formed around it because this will be getting charge. And remember, so much physics in the same small looking thing. When you have the bristles of this comb in a shape like this, charge density will be very high here and charge density will be slightly less. This forms what you call a non-uniform electric field around the comb. Maybe it's looking heavy for you, but don't worry. Since you asked a question, I have to tell you the correct physics of it. So this non-uniform electric field will create a dipole here, apply a force also. That's why this whole thing moves. There are many dipoles here. On the dipoles here, this electric field will apply force and torque. So it might twirl a little and as well move forward. That's what is going to happen. This is the physics modeling. Try to understand. Ramya, tell me now. I'll come back to this in a mathematical way, Amma. Don't. It's not just some silly talk here. Everything is put in the mathematical form. So I don't know whether you understood something extra after my discussion. Could you tell me if you followed something?
So when we rub the bristles of the comb, an electric field is formed because it's getting charged.
Yeah, that electric field also is non-uniform, Amma.
It's non-uniform.
Why? Because near the pointed edges there will be charge density is higher.
Yes.
Flat surfaces charge density is less. If I have a sphere, Ramya,
Yes.
which has got same radius of curvature, and if I give charge, field will be somewhat like this. Even this is non-uniform but symmetric. But here, some non-uniform, non-symmetric electric field is formed. That is a key, remember. So,
yes, sir.
Yeah, that will do what in the paper?
So that attracts the negative charge in the paper.
That creates dipoles, you should say.
Creates the dipole.
Dipole is a single unit with plus minus together.
Yes.
Creates dipoles and applies what? Force and torque. That's why you can see the papers move also, but also a little turn, rotate if you can watch it.
Yes, sir.
So much physics. Everything will be converted to maths, Ramya. Just remind me sometime later when I discuss dipoles.
Okay, sir.
All right. So these 9 or 10 examples. Yesterday, how many we did actually? I don't remember. 6, 5 or?
We did 4, sir.
4 only. So today, did they give any double number here? 5, 6, 7, 8, 9. Something else I'm missing. Anyway, it doesn't matter. We covered almost everything. So this is the what you call curtain raiser for the unit called electricity and magnetism. Now, before I continued, I would entertain your questions. Any basic level question also you can ask. Guru Charan. Keep your audios muted. We don't want to hear the talk in the room. Right.
Sir,
Yes, tell me.
sir, in the example of the 2 wires,
Yeah.
Means in that 2 wires, does the dipole means there is no presence of dipole?
No presence of electric dipoles, you mean to say?
Yes, sir.
No.
Since
This is a
the
metal
electrons
wire.
are flowing.
Guru Charan, that's a metal wire. in which there will be free
Yes, sir.
electrons which are moving to form current. The metal will be something like this, children. This is like a grid-like structure. You can think of a metal. Like you put one over the other like that. Where the crossings are there, you got the ion cores. And in the empty spaces, free electrons will be moving. That's a model. So there's no dipole as such. In your chemistry, you call it metallic bonding. Metal structure will be like this. Like that, you keep drawing many lines. At this corners, you got your positive ion cores. Do you understand the meaning of positive ion cores? Copper, if I take, copper's atomic number is 29. 28 electrons will be forming the ion core, and one single electron will be there free. So in a copper crystal of some millions of atoms, millions of free electrons will be going through these spaces, and they form what you call the current in a wire. So there's no dipole. Okay, Sai Bharat, any question? Okay.
Sir,
Yes, Pawan.
a question in the comb example.
Tell me.
Sir, a comb run through one's hair attracts a bit of paper, but when our hairs are like wet, then they don't attract bits of paper. Why?
You require a little more of physics there. Like what happens with the water there. You need to know something more than this, actually speaking. For a dry hair, it is easy to transfer charge, not with water. Water is like a dielectric. Water is like an insulator. Try to understand. The whole idea of charging is what, Pawan? You need to transfer charge from one place to another place. Water is not a good conductor. What do you say?
But water containing salts can conduct electricity.
You can okay, so you mean to say you would like to have salt water? Don't deviate too much. Okay, next question, please. Related to the things we have here, okay? But no, actually, real physical situations are more complicated than what we think. We try to give some kind of an explanation, but you need to know much more physical models to do that. Okay? Yeah, anybody else?
Sir,
Yeah, Anshuman.
sir, if we rub with our scale, with our like when we have oil on our hair, sir, and
No,
we
oils, no
take
water.
our
No, you're deviating.
scale.
Oil, water, just forget right now, because I told you already. You need to know the oil also is dielectric. Once again, do you know? Oil is dielectric. What is a dielectric? That is insulating material they are. So they don't allow easy charge flow. Okay. No, actually, I want you to talk in what I've talked, because ultimately, what will you use in the exam? Each of these 9 or 8 examples I've given will be converted to problems and formulas. So I want this kind of things, actually speaking. There's no difference between oil and water as far as the insulating property is considered. Rishita was saying something. Rishita, tell me.
Sir, the dipole that is created in the paper,
Yeah,
as you said, has positive and negative charge.
the
Both.
single unit it exists, Amma. Yes.
But in chemistry, we learned that there is partial positive and partial negative. That's what creates the attraction.
What do you mean? Don't worry about partial negative, partial positive. Fine. Ultimately, it is electrically speaking a negative charge and positive charge. Huh?
Yes, sir.
There's no need of the word partially has no meaning there.
Okay, sir.
Electrically speaking, for the electrical property, plus delta minus delta, that's enough. And I don't know why people call it partial. Actually, I really am not very interested in that. Finally, some plus delta and minus delta. Okay,
Okay. Yes, sir.
that's what is important for electric field.
Okay, sir.
Right. Next one. But I'll talk even more. One main question people keep asking is, people keep on giving some kind of explanations which are not good. This question, why only moving charges form magnetic field? Or why moving charges only form magnetic field? This is a question which bothers many people. Why moving charges only form magnetic field? This has to be understood in a simple way, proper way. Look, I told you in the beginning itself that the idea of field or the requirement of field is there because we would like to explain action at a distance forces. Because our idea of forces is based on touch. I hold this bottle and develop friction between my fingers and the bottle so that I oppose the weight of the bottle. So friction between my hands and the bottle is balancing the weight of the bottle, so that's why it is not falling missing. So the idea of force basically to begin with is connected with touch, contact. But force acting through spaces, we need to give some kind of an explanation. For that, our scientists devised a mechanism called field. Which means there will be as many fields as the types of forces you have. Types of forces means, like for example, I'll tell you. This force between one electron and another electron is something very special force. This is acting along the line joining the particles. This is called a central force. What is that word I use, children, here? Central force. That is a force which acts along the line joining two particles is called a central force. If these two electrons are left alone like this, they'll move away like that. If there is a nucleus here, around it, when electron goes, every time the force is towards center, along the line joining the center of the nucleus to the electron. But yes, when an electron is stationary here. If one electron is brought near it, it will be repelled like this if it is put here. But if this electron is in motion, if another electron is brought and put into motion, it doesn't only get reflected, it doesn't get only repelled, but also gets deflected. That means another force has come. That force will come only if this electron has a velocity. And this particular force is completely different from this central force. People found that this force is always in a deflecting direction. For example, if electron is going that way, this magnetic force will be this way. Like that, it goes on deflecting the electron. If this electron was stationary here, no, let me say, yeah, doesn't matter. Like BF should introduce. I'll tell you. A moving. See, if I have a current carrying wire, let me say there is a magnetic field around it. We said no. That field will be somewhat like this. If in such magnetic fields, if I project charges, there will be all the time, a force will be acting all the time which is perpendicular to the velocity. So which is different from this force which is acting along the line joining the two particles. This force and this force are different. So people observe two forces, and they attributed those two different forces to two different fields. That is the whole idea. Supposing you did not name it as electric and magnetic fields, you could have named it as field A and field B. One force comes because of position alone. One force comes because of velocity alone. If velocity is there,
Hello.
I'll tell you. Just a minute. I'll rub this off.
Hello, sir.
Yes.
Sir, please can you repeat? There was internet issue. That's why I had to reconnect.
Yeah, I'll tell you. Just a minute. I was telling you there are two kinds of forces for the electrons, for the charges. If they were stationary, electron, for example, another electron placed here will be simply repelled. But if I have a magnetic field, for example, I'll tell you the known magnetic field for north and south. If I place an electron, there's no force. But if I project it like this, with a velocity v like this, look, there will be a force which is acting perpendicularly towards you like this, which is perpendicular to the velocity. It's a deflecting force, we say. Whereas this force was acting towards origin. If this, I say this origin of the charge here, source charge here, this force will be acting like this. Whereas this force will be not acting towards anything, towards no center, nothing. It will be all the time acting perpendicular to the velocity. So there are two kinds of forces the charged particle experience. So there are two kinds of fields. One field may be electric field, the other field may be magnetic field. And remember, if there is life possible on some other planet, like Earth somewhere, maybe they'll be dealing with this two forces, electric and magnetic forces, but they may not have called it electric and magnetic. Somebody might say one force is force X, the other force is force Y, that's all. This X comes because of position, Y comes because of velocity. So that is the difference between electric field and magnetic field. So just write down few statements. I'll dictate them to you people. What is electric field? The question is, I'll just mention here. What is electric field? If in a region of space, an electric charge or a charge, let me see, a charge experiences a force just because of its position alone. There is electric field in that region. This is the most important. Just because the charge is there at some position R from some origin O, and because of that position there is a force acting on it, definitely I will say that there is in that region electric field is there. And remember, this electric field is also caused by another charge by virtue of its position only. By virtue of its position only. So this is about the electric field and the cause of electric field. The fact that an electron is there in space, it has got electric field around it. Whether it moves or not, that's not an issue. Even if it moves, there is electric field. Even if it is stationary, there is electric field. That's what I mean by virtue of its position alone. But what is magnetic field? I'll tell you what is magnetic field here. What is magnetic field? If in a region of space, if in a region of space, a charged particle experiences a force by virtue of its motion. By virtue of its motion, in that region, there is magnetic field. And remember, this magnetic field is also formed by another charge because of its motion. This magnetic field is also caused by a charge because of its motion. And remember, this force is different from that force. That is a central force. It's a conservative force. This is a non-central force. That means there's nothing like an origin to which it keeps acting. It all actually keeps acting every time perpendicular to the velocity of a particle. So to differentiate, to distinguish between two kinds of forces the charged particle experience, people introduce two fields. One is magnetic field, the other is electric field. Come on. Did it become too heavy for you? I don't know. Sai Bharat, Ramya Manasa, Rebecca Rose, and Guru Charan, and Rishita, and who else? Srihit. Tell me.
Yes, sir.
Is it becoming heavy? Don't worry. Just feel free, be free. Try to enjoy it more than trying to understand it too much. Just the words which I speak, actually try to keep saying them in your mind again and again.
Sir,
Yes, Guru Charan.
sir, in this definition of magnetic field, what is the difference between two sentences?
Two sentences, Guru Charan. Can you read?
Sir, the first sentence is of 4 lines and the second sentence is of last 2 lines.
Please read them, because then I'll put all the yeah.
Okay, so the first sentence is, if in a region of space a charged particle experiences a force just because of its motion, there
In
is
that region,
magnetic
we say
field
there's a
in
magnetic field. But who formed
Yes, sir.
magnetic field, Guru Charan? Somewhere else, there is another charge moving. That moving charge is forming this field. This field is applying force on this moving charge. There's a source charge, there's a test charge. The source and test have to be really understood, children. The whole lesson is based on, the whole unit is based on this source of fields and the fields applying force on test charges. The first statement, Guru Charan, is about force. It's about the force experienced, and that reason is field. Second statement is about cause of that field. Both are charges only. Come on. Anybody else? Sushma Vaddepalli and SD7CCB5A. Can you tell me your name? We have not gone into that Orwellian world where the people are known by codes, children. We have our own names given by our dear parents. So 5D7CCBC5A. Tell me your name. And Bachu. Praharsha, what's your name? Sai Bharat?
Devarchit, sir.
Okay. Children, All right. Anshuman, Srihit, Sai Bharat, Rishita, Rebecca, Bachu, Gurucharan, Deepu, Sushma Vaddepalli, the code 5D7CCB5A, Pavan, Uday, over. All right, children. So I want your feedback. Manasa, even if you did not follow full, Manasa, tell me what is that you follow. Let me listen to you. Because after this, we are ready for the lesson. Of course, you're not, yeah, Manasa.
Regarding electric field,
Yeah,
a charge experiences force only because of its position.
yeah. And it forms field because of its position.
Right.
Yeah, a charge is there in space, Manasa.
Yes, sir.
Whether it moves or doesn't move,
As a move,
it has got some
field.
aura around it. Huh?
Yes, sir.
Some halo around it. Do you understand English, all of you?
Yes, sir. And
So, by virtue of just being there, a charge, a net charge there, it has got a field around it, which is called electric field.
yes, sir.
And what is the meaning? What is the idea of this having this electric field, Manasa? If there was another charge in that region, whether it moves or not, it experiences force because of that surrounding aura. That's the field.
Yes.
So what is important there? Position is important to explain electric field. Then the second one, Manasa.
Regarding magnetic field, a charged particle experiences a force
In a region.
in a space or a region.
Yeah. Because it has got a velocity. That
Yes.
means.
Only because of motion.
Yeah, only because of motion. That's correct. But who will form this magnetic field, Manasa, again? Another charge somewhere, source charge. It will form a field called magnetic field if it has got a velocity. But don't think I'm just going back and playing with words. What I was trying to tell you was, what practically we know is force. And there are two types of forces. One force along the line joining, the other force which comes only with the velocity and then perpendicular to the velocity. So two different kinds of forces, so two different kinds of fields, that's all. Magnetic and electric is just historical in nature, nothing else. Uday, have you got any question? There are two kinds of forces for charges. To account for two forces, you've got two fields, two names. For example, the first electric field could be called Manasa field, and second field can be called as somebody else's field, for example, Rebecca's field. That's all. That's all about magnetic force and magnetic field and electric field. In fact, for you to understand, I'll give you the most important relationship in electromagnetism. The electromagnetic force, F equals QE plus QV cross B. See, remember, I'm just trying to summarize some equations, children, here. When I talk like this, without apparently any preparation, remember, there is a mathematical scheme in the mind which is being elaborated. Look, charges experience force. This will be there even if the charge is at rest. But this force will be there if charge is only having velocity. This constant is called magnetic field. This constant is called electric field. One force is proportional to Q, which is stationary. So the proportionality constant is electric field. One force is proportional to Q, and as well some V component, V perpendicular. So that proportionally constant is what we call B, magnetic field. So Mansa seems to be okay with that. What about you, Rebecca?
Yes, sir.
All right. No, even if you're not completely comfortable, don't worry. But there is something like this, just get that good feeling, then things will happen in a simple way, believe me.
Yes, yes.
Sushma? Anybody else, boys? Srihit? So this is going to be my introduction for the whole unit called electricity and mechanism. Children.
Yes, sir.
So as I told you, remember, these 4 statements should keep coming back to you again and again and again. Sushma, which college are you in? Sushma Vaddepalli?
Sir, Navodaya.
Navodaya, JNV. From where?
From Karimnagar.
Karimnagar, Choppadandi.
Yes, sir.
You are doing 12th there now?
Yes, sir.
Okay. How many children are there in your class?
43.
43. All science students or commerce also you have?
Only science students, sir.
Only science. MPC, most of them.
MPC, yes, sir.
So you finished all the first year physics there? All the last physics, rotational motion, gravitation, all that?
Yes, sir.
Did you hear a word called central force previously?
No, sir. Centripetal and centrifugal I have listened.
That's
Central
all.
force I didn't listen.
Okay. Gravitational force is central force amount. It also acts along the line joining 2 particles. Whereas this magnetic force is not like that. So there are 2 distinct kinds of forces. More you will understand as I keep talking, giving you the mathematics of it. But see if you like the idea that there are 2 fields. One field is to explain one kind of a force. Another field is to explain another kind of a force. So the magnetic field and the electric field names are all simply historical accidents. You could have called them whatever field you wanted. Sushma?
Sir?
Yes? Anybody else? Yes, Pawan? Tell me. I told you already, my class works wonders for you people, provided you speak.
Yes, sir.
Full freedom to ask. Somewhere, for example, if you're deviating a little, I'll stop you deviating. That's my duty anyway. But no rules for asking questions. You can just raise a hand and I'll give you time, you ask. If you're definitely deviating, distracting, getting distracted and going this way, that way, tangentially, not focusing on that, I'll say we'll do it later. Or I'll tell that's not required. But when I say that, don't think bad, because sir told us to ask questions, but he's not answering. So I would have to decide which question to answer. Otherwise, it will be free for all and we won't be doing much. Okay? But questions are entertaining. All right, children? Because the next lesson is once again going to be lengthy. I will stop it here. I want you, we are posting these videos for a while for public, because I wanted people to see what's happening here basically.